Here again is that geometric series. So long as x is between -1 and 1, then the power series, where I take all the non-negative powers of x and add them all up, that series will converge. And that series converges to the following formula. It will be 1 divided by 1 minus x. So for right now, I'll call this f of x. Now, what can I do with my newfound knowledge? Well, if I want to, say, determine a power series representation of the function, I want 1 divided by 1 minus x, but I'm going to square that denominator. For whatever reason, I would like to have a power series representation of this function right here. Now, I can't do my same trick as I did in the slides of my substitution, right? Because this is going to look like 1 minus 2x plus x squared in the denominator anyway. That's not going to work. However, the derivative of my function, f prime of x, this is going to be, thanks to the quotient rule, I'll have my denominator squared. I have to have original numerator times derivative of the denominator. And I've got to have original denominator times derivative of the numerator. Oh no, what order do they come in? So when we are calculating the quotient rule and our function looks like hi over ho, the formula is ho-de hi minus hi-de ho, square the bottom, and away we go. So that tells me denominator times derivative of the numerator minus old numerator times derivative of the denominator. Oh, look at that. It's exactly the function that I want. So if I want a power series that represents this rational function right here, all I need is the derivative of my geometric series. And I know that I can do my differentiation on each summand by itself. So this is something that is very special about power series in their interval of convergence. I need to be very careful about how I say this. The trick I'm going to do next only works for power series. Power series are very nice to work with, and we get to move derivatives inside and outside of the power series, but only as long as that power series converges, and only because we're adding up powers of x. This does not work with other kinds of infinite sums. And for that reason, we don't talk about other kinds of infinite sums, at least not in Calculus 2. There's a beautiful world of adding up infinitely many functions to get some new function. And a lot of that we're going to leave outside of the purview of this class because it gets very dicey about whether or not those things work and under what circumstances they work. So for right now, we work in power series. And in power series, I can say that the derivative of a sum of a bunch of things is the same as the sum of the derivatives of a bunch of things. And so how do I calculate this? I'm going to bring my exponent down as a coefficient. New exponent is 1 less. So this power series is then going to start 0 plus 1 x to the power 0 plus 2x to the power 1 plus 3x to the power 2 and so on. Okay, well, I can throw away that 0, right? My first term in the series is a 0. I can just get rid of that. So my derivative is then going to have this formula. If I start at n equals 1, go to infinity, I'm going to have x to the power n minus 1 with a coefficient of n. So this power series is the derivative of the power series I started with, but only inside of that radius of convergence, only inside my interval. So all the calculations I'm doing require this assumption right here. Working with a power series in this way is only valid on the interval where that power series converges. So as long as x is between -1 and 1, this power series formula that I just came up with will be equal to 1 divided by the quantity 1 minus x all squared. Outside of that interval, you get nothing. The series diverges. The infinite summation does not give you a real number. And at that point, we can no longer talk about derivatives and continuity.